So they have to have some way to manage the fleet and make sure it's reliable and safe.
Yeah, thanks for that, Doug. Thanks, Doug. Yeah, so Mitch, I think, hit on a key phrase at the start of the day today. That was multi-physics. Think about all the physics that's involved. We got electrical phenomena, we got mechanical phenomena, we got fluids, we got all kinds of things going on. So, electrical phenomena like torque ripple becomes, if we're not careful, that lines up with structural resonance, like Doug talked about. Structural resonance leads to durability problems and strength problems, whatnot. So what I want to look at now is just briefly look at the challenges related to durability and reliability in the eVTOL world, and hopefully point out some solutions along the way as well. So how do we improve durability and reliability of an eVTOL aircraft or a fleet of them? So the way we need to look at this is, challenge one is strength and durability. How do we make sure these things are strong enough to fly and durable enough to continue to fly? And that's not just a question of the traditional airframe guys. This is not just an airframe question. This is really a question for all kinds of things in the aircraft. The battery system, the heat exchangers that go with the battery system, landing gear. Some of these are new to eVTOL. Some of these are old components, old structural components. Landing gear have been around for a long time. But just the same, we have to be able to understand their strength and their durability so that we have a solution that will continue to work over time. So how do we approach this question of durability and reliability, or strength to begin with, for example, strength and durability? Now we have a lot of CAE-based simulation tools at our hand, available to us to use here. So the question is, how do we balance out simulation, say structural durability simulation, and physical testing? A good friend of mine, brilliant engineer, said, let's predict what we know the physics about, and let's test where we don't. Let's test to verify. So really, we look at this in two ways. These days, an engineer can approach this question of strength and durability. First off, is let's model what we know. In other words, if we can describe the physics, of how this thing resists, say, dynamic loading or torque ripple or flight maneuvers or whatever, if we can understand that physics, then we can use CAE tools like finite element modeling and fatigue life prediction and such early in the design stage, so we can design durability into our parts, right? So we can quickly assess durability and strength and such, which means then we can build durability and strength into our structure. So when we do get to testing, right, we have to do verification tests. We know this. When we do get to testing, we have an increased chance of success, right? So we're trying to improve the confidence of success, because there's nothing that's going to take more time or money than finding out that a product we've prototyped and we test fails, right? That's what we don't want to have happen, the build it, break it, fix it loop. We want to build durability and strength into our parts as early as possible as we can using virtual tools. Right, so an example of this virtual, let's model what we know, or where the physics is understandable. Let's use numeric simulation to help us. Here's an example of that. This is an example of predicting the durability or the fatigue life of this structural part. Okay, so we start this. This is finite element analysis up here. So how does this structure resist load, whether that's dynamic load or static load or thermal or whatever it is? FEA, finite element analysis, can help us understand how loads become stress. But nowhere in a design spec is the line that says keep the stress below 600 megapascals. The spec will say something more like it has to last 25,000 flight hours. So then we need to start thinking about bringing in fatigue loading, so get from strength into fatigue life. So we're doing this virtually, right? We'll rely on testing later for verification purposes and also for correlation purposes. But if we bring this known physics of failure, this fatigue concept, this fatigue failure mode, if we bring this early into the design process, we can iterate on this design very quickly and make sure that we optimize the product for strength and for durability. Okay, because the next challenge around the corner, once we have one of these things flying, the next challenge is lightweighting. Okay, so through grace of God or through some stroke of luck or whatever it is, we have an eVTOL aircraft prototype that flies. That's awesome. Okay. So the cool thing is now we understand its performance environment. We understand its vibration. We understand the mission, in-service loading and such. But we need to now think about how do we improve performance, reduce weight to improve range, for example. Okay. So this lightweighting challenge of design B, next design revision, how do we optimize its strength and durability? How do we optimize its performance without impacting strength, without sacrificing durability? Okay. So we want to bring this durability analysis into the redesign loop so that we can effectively lightweight. And we're going to look at how we could use this tool called ENCODE from HBK, fatigue analysis software, to help us with this redesign loop. Okay. So like we said before, we're going to model what we know. If you understand the physics, we're going to try to bring the modeling of that physical behavior, that durability, that strength, that stiffness, whatever it is, try to bring that as early into the design process as we can using computer simulation. And the physics that we don't understand, we'll test. And also even the physics that we do understand, we'll test to verify at the end. Okay. Which then raises the next big challenge, which is how do we durability test these aircraft? Okay, really complicated loading, really complicated vibration. As Doug and Mitch both said, one of the challenges with eVTOL is that for a variety of reasons, they're typically prop driven, and returning to props has brought up some engineering problems that the aerospace world has faced in the past, but has kind of grown out of through the godsend of the turbine engine. Here in this case, now we have a prop engine. We have a prop based, which creates really complicated loading. So how do we do structural durability and strength testing in this environment? Validation procedure is going to be this: let's measure or predict in-service loading. Right? There are ways we can measure using HBK sensors and DAC, the kind of stuff that Mitch talked about earlier. There are all kinds of ways these days to numerically simulate aerodynamic loading to predict loads and such. But either way, we need to understand what's the operating environment in terms of load, pressure, strain, these kinds of things, right? And then we can reproduce those conditions in the test lab, and we can accelerate the way we do that such that we can look at assessing, say, a 10-year life of the aircraft without testing for 10 years. Okay, so we can accelerate that testing loop. Realistically, what these tests look like is kind of what you're seeing here. Lots of servo hydraulic actuators that are used to replicate, say, the aerodynamic loading or vibration loading on different parts of the airframe. We're looking at an airframe test here. We'll talk about component level, smaller stuff in just a minute, which is important because these days, we have batteries that are subjected to vibration. We don't want that to fail. We have inverters, we have heat exchangers, we have all this stuff, eVTOL specific stuff that we now need to think about the durability of, not just the airframe. This type of full scale or even smaller scale testing, could be done in a static way, right? Static testing, how strong is this wing in a static sense, right? Or it could be done in a fatigue testing, durability testing, where we have repeated blocks of cyclic loading over and over. HBK has just a ton of solutions to help in this environment. Sensors, load cells, strain gauges, accelerometers, data acquisition hardware, all kinds of solutions to help with this, including software to analyze and track trend during durability testing, how our loads or strains changing. Hopefully the loads input aren't changing. That should be a part of the controlled test loop, but resulting strains, we can use that as an indicator of structural health and help us understand how the test article itself is behaving as the cyclic loading continues. So that's kind of airframe testing. That's big stuff. Let's look at smaller stuff, because at some point you're going to be faced with the challenge of how do we know the battery tray is not going to fall out? How do we know that the heat exchanger that keeps the batteries cool isn't going to leak, isn't going to break? Okay, the way we do that these days, we often use like a vibration electrodynamic kind of a shaker rig like this, where this is capable of moving this table back and forth, right, and reproducing the vibration environment that the aircraft feels, but we can reproduce this now in the controlled environment in the lab. Okay, so these test rigs are awesome. HBK makes some of these under the LDS name. But the question is, what shaker profile? and for how long, right? So these shaker tables do an awesome job of reproducing vibration. Now, should that be reproducing PSD random vibration, swept sign vibration, a combination of the two, sign on random, swept sign on random? Yeah, there's even random on random now, like two narrow bands of random together. And how long, right? How long? So we're going to look now at ways we can use this what we call ENCODE software to take measured vibration data and convert it into what we call an equivalent damage accelerated shaker profile. And that may be a random PSD, it may be swept sign, sign on random, swept sign on random, lots of different ways we can do this. The key is this is potentially thousands of hours of vibration being collapsed down to maybe tens or hundreds of hours in the test lab, so we can run this shaker and reproduce the vibration environment of thousands of flight hours in tens or hundreds of lab hours. Now you may say, hey, wait, hang on a second. This really isn't that hard. This shouldn't be that hard because there's all kinds of different specs for shaker profiles, right? RTCA and DO 160 and Milstan 810, all these have different specs on a rotorcraft experiences this GRMS level, so on and so forth. Fixed wing does this, so on. But hang on a second. If those specs talk about rotorcraft and fixed wing as being two different things, right? Two different things. eVTOL is a weird combination of the two, right? So we really need to think about how, if we want to replicate a vibration environment that the eVTOL itself experiences, it's probably not as simple as it's either a fixed wing aircraft or it's a rotorcraft. It's some combination of the two. So let's go measure vibration in flight tests and use that to create shaker specs that are meaningful to your actual aircraft, which is an amalgam of rotorcraft and fixed wing behavior. Okay, that way we can make durability tests that really make sense. So this shaker rig here is shaking things in a way that the actual aircraft shakes them, and we have greater confidence in this durability validation test being correlatable to in-service loading. All right, last thing to look at here is reliability. Okay, so durability I like to think of as a structural problem, and Doug talked about this with torsional vibration and first bending mode and all this kind of stuff. Okay, terrible things can happen if we're not aware of those. We're going to move out of the structural side now and look at reliability instead, which is reliability is literally what's the probability that this thing can keep doing its thing to a certain amount of time, to 30,000 flight hours or something like that. Okay, so we're going to end up using this concept of reliability two different ways. One is when we're designing or developing a new product. So blank sheet of paper, we do an FMEA to say what are critical failure modes we ought to be aware of when we're designing an eVTOL aircraft. In the product development world, we're also going to use this thing called a fault tree diagram, right? And the fault tree diagram essentially is a way of trying to find those single points of failure that Mitch referred to earlier, right? We don't want to be surprised by these single points of failure. So we essentially break down the entire system into, here is a fault. Here's something that could happen. The brakes could shut down or whatever. Flight control could be lost or whatever it is. And then, so this is the effect up at the top. And then these are causes that filter on through. And this is a really simple fault tree diagram I've got here, just because we will try to keep things simple so you guys can actually see it on your screen. Realistically, an eVTOL subsystem, system, or entire aircraft could have hundreds or thousands or even tens of thousands of these little causes filtering all through. Okay, but this is a way then of being able to recognize where are those single points of failure. Where are those single points of failure? Okay, so this is going to be really, really, really important for us to recognize up front and use this as a tool to design reliability into our aircraft. Second way reliability comes into play is in fleet operations. So let's just say, skip ahead like 5-10 years, whatever it is. Let's just say that your eVTOL aircraft are certified, they're flying. You've got a fleet of air taxis now. Okay, let's just say you make it that far. I hope we all do. Hope we all can. So we have hundreds of these air taxis flying around. That's great. Next question is, how do we keep that fleet moving? How do we keep that fleet alive? It really comes down to trying to answer the question of how do we keep that fleet available? And also, how do we address its maintainability? All right. So what we've got here, this is a reliability block diagram of a series of parts and how they interact together, and how time to failure or mean time to failure or reliability data for each component is cascaded or combined into reliability of the entire system. We have some pieces here that have redundancy built in. In other words, if this one fails, this one can continue to work. This is not a redundant part. If this fails, then this entire flow, this entire system shuts down. Okay. So if we can recognize how all these different systems fit together, or components fit into subsystems, into systems, how they all fit together, then we can start to think about how do we maximize the ability of this thing to keep doing that. In other words, our fleet to keep flying. We can think about maintainability and how do we schedule maintenance to maximize flight uptime and to minimize cost. So this might be a little ways out for you. If you're, in the design phase, you might be more over here trying to recognize where is risk. But at some point, when your fleet is flying, then we'll have to think about how do we keep that fleet flying in an optimal way. Okay, so with that in mind, let's just summarize here. Let's just summarize here quickly. What we just looked at is really kind of the competitive, odd, tricky engineering landscape of the eVTOL world. Tons of promise, lots of open design space, but some challenges that came with it. Challenges like how do we maximize the performance of the electric powertrain, for example. Mitch talked about that. How do we manage noise and vibration, both from a structural certification and noise perspective, but also from a public acceptance perspective as well? That becomes really critical. And then I followed up here. That was Doug talking about that. And then I followed up here with strength and durability, lightweighting, and reliability as challenges. But so tricky environment we're in here. eVTOL world is new, exciting, kind of daunting at the same time, right? So some new challenges. Propellers have brought back some old challenges. But in spite of that, just remember, HBK has a lot of solutions to these challenges. Okay. All right. HBK, we're not going to certify anything for you. We're not going to design stuff for you, but we've got tools that'll help with all this. We've got tools all along. I hope you've seen challenges, but also solutions as well today.
Thanks, everyone.
Thanks, guys.
Bye.
Cheers. Bye.